Hello and good morning. Greetings from Garching. My name is Dirk Petry. I'm an operations scientist here in the ALMA Regional Center, and some of you might know me already. I've already given an iTrain talk some time ago, and today I'm going to present to you our new UV coverage assessment tool, AssessMS. It has already version 3.0, so you're not getting something extremely new. Yeah, let me now start and give you some background. So, as you know, ALMA, when it takes data for you and produces the data product, it's trying to optimize various aspects of your data according to your requirements. And that is, of course, the calibration quality. It's the overall sensitivity and the angular scale coverage. So what is being checked in the quality assurance is the minimum and the minimum angular scale that the observation is sensitive to, also called the angular resolution, so the synthesized beam size. And we are looking at the beam shape, so how elliptic it is. But until now, we're not really looking at the shape of the synthesized beam for individual angular scale ranges. And we are also not really assessing on a per MOUS basis the maximum recoverable angular scale, so the other end of the range. And because of this, I mean, the ALMA project has been aware of this for a long time, obviously. And so in January 2020, more than 5 years ago, we started off an internal development study to take care of these last two parts that are kind of missing in the scheduling and QA. And that was a development study that was led by myself and Maria Diaz-Trigo, and there were many contributors, Rüdiger Kneißl, Ignacio Toledo, Stefano Facchini, I've forgotten the first names, Atsushi, I think it's Miyazaki, Toshibu Takagi, Ashley Barnes, and Francesca Bonanomi have all contributed to this over the years, and I would also like to underline this here and thank them. Without them, AssessMS also wouldn't exist. The results of this development study were published in two speed papers that you can find on Archive. And there was also a final report at the end, obviously, and that was published in August last year. And the results also included a whole big suite of software products, and among them was AssessMS version 2. And then we went on and develop that further, and I'm going to come back to this, but just to give you a teaser, so the description of version 2 was already contained in the final report of the development study, and that was, of course, initially only intended for internal use in ALMA quality assurance. But now we have gone further and produced a public version with many new features that is called AssessMS 3. And you find the documentation and the download link and everything at this link here on the slides. I encourage you very much to go there. So what I'm telling you in this talk is it's not going to be everything that's actually mentioned on this page. The talk would be too long. And so what is AssessMS? It's a set of Python modules. One of them is called AssessMS, but there are also several support Python files. One of them is MS-Histotools and so on. And they all need CASA 6.6.1 to run. And the general idea is that you have a set of measurement sets that you want to assess together as one data set. And you run AssessMS on it, and you get a set of diagnostics consisting of plots and text files that tell you about the quality of the UV coverage, comparing it to a theoretical ideal case. So this is what the talk is about. Here's the outline. So first I want to motivate a little bit why you should care about UV coverage, but I suspect many of you know this already, otherwise you wouldn't be here. Then I'm going to get into the new features that SSMS 3 has over the previous version, and then I'm going to give you essentially a run over the documentation. So I'm going to start with the output, because that's going to take longer, and then at the end, the usage is actually very simple. And at the very end, I'm going to go over one example in the context of data combination. So an example running on a group ops unit set. Good. Then I'm moving on. So what is the impact of the UV coverage of your data set on your science results? Obviously, it's a big impact. And getting really perfect UV coverage is nearly impossible. It's very expensive. You would have to have a lot of antennas. What is shown here is a simulation of an ALMA 12-meter observation in configuration 1 with the default value of 43 antennas and an elevation near 90 degrees. So the array is looking up. And you have essentially perfectly circular UV plot with an outer edge and an inner edge that tells you the longest and the shortest baseline indicated by these two circles. But already in this pretty perfect setup, you can see that there is incomplete coverage. You have gaps here at the longest baselines. Some of these tracks are incomplete. And of course, you have the inner short spacing hole. But when you really look at what angular scales you are sensitive to, then you already have to cut down on this. So the outer and inner edge of this does not give you your angular resolution and your maximum recoverable scale, but you actually have to look more at the L80, so the baseline that is longer than 80% of all the baselines, and at the LO5, so the baseline that is longer than 5% of all the baselines. So they really determine, at least for ALMA configurations typically, what is your minimum and maximum recoverable angular scale. And if you then go to a more realistic case, with a short ALMA observation, so what we had previously was 1 hour, this is now 38.5 minutes of a real ALMA observation in configuration 5 with 48 antennas, but not looking at the zenith, but more at 60 degrees elevation. And you see we are already, even though it's quite symmetric somehow, it has huge gaps all over the place. And especially for the long baselines, the longest baseline as a number doesn't really tell you much. And okay, this is a very long not a very long, but a long baseline observation with, I think the longest baseline is something like 1,500 meters. So you can't really see the inner edge, but the LO5 would be around where this red circle is. I haven't virtually measured it. So now what do all these things you can know about your UV coverage actually have in terms of impact on your science results? And here our development study made quite a big effort to try and quantify this. So we looked at various simulations, for example, such Gaussian blobs in various patterns that we sent through simulations of different UV coverage. So here you see, can you actually see my pointer? I hope so. So here on B, you see an output of an simulated observation with quite good UV coverage. So we're more or less reproducing the input, but with insufficient UV coverage, you can see that the resemblance to the so to speak, truth is very bad. some things are nearly gone, some features. It's no longer rotationally symmetric and so on. Same here for these stylized protoplanetary disks. So with good UV coverage, you're recovering this quite well. But with worse UV coverage, you are introducing these asymmetries that are not really there. So here, this bright feature, for example, might be interpreted as something scientifically. I mean, in reality, you don't know what is the real truth. So you might interpret this as something, but it's a total artifact of your UV coverage. And then finally, we also looked at real ALMA data cases, for example, the observation of a protoplanetary disk spectrally resolved. And we played around with flagging different parts of the baseline length distribution. At this point, I want to introduce this concept here. So the baseline length distribution is simply a histogram of the weighted visibilities as entries into a baseline length histogram in 1D, or you can also have it in 2D, where the baseline orientation plays a role. In this case, we have only deformed the baseline distribution in 1D. So we took away sensitivity in certain sections of the distribution and put it elsewhere. Because, of course, deforming the baseline length distribution in this context does not mean just taking away information. You have to keep the overall sensitivity constant in order to be fair. So we are comparing here different shapes of UV coverage with the same overall sensitivity. So we called these deformation cases, or we designated them with these capital Latin characters. A was ideal, B, C, D, E were these various defects that we introduced. And the other concept I want to introduce here is this filling fraction. That is essentially the ratio in an individual baseline length range of the observed baseline length distribution entry divided by the expected one. And okay, what is the expectation? The expectation is something that I have to refer you to the texts that I mentioned, the publications from the development study, but just briefly, the expectation, at least for the ALMA 12-meter array, is a tapered Gaussian that has essentially two parameters, or three parameters, if you like, which is the angular resolution, the maximum recoverable scale, and the overall sensitivity, so the normalization of the whole thing. And so you can see here there's on this, so if we introduce this defect, there's a very nice match here for the long baselines, but then we have this shortcoming of short baseline sensitivity, and the excess, I mean, the sensitivity that was taken away here was essentially put on the other baselines. And the same is true for the other cases. So when you do this, for example, to this real data set here of a protoplanetary disk observation, and then repeat a scientific analysis and compare the original parameters that you get from some model fit, for example, here, this vertical position of the emission surface on the protoplanetary disk as a function of the disk radius, has this model here has four physical parameters: z0, phi, psi, and r taper. And so these four diagrams here show you what happens to them when you introduce these defects into the UV coverage. And you can see, so this is the value if you have no defect, and for reference, it's repeated here for all the four parameters, psi, z0, phi, and this is actually mislabeled here. This is, sorry, this ignore this diagram. This should be replaced by the one for R taper. But anyway, What you see is as the size of the deformation increases, the um, the parameters that you get out of the fit start to deviate from your reference more and more. And it depends on the location of the defect, how big the deviation actually is. Some parameters are less sensitive to these BLD deformations than others. But altogether, when you go beyond something like a deformation of 75%, then your systematic errors that you introduce by this deformation are much larger than the systematic errors. So what we've learned from this is altogether, we find that imaging is quite robust to azimuthally symmetric BLD defects. So a filling fraction of only 0.5. So if you have lost 50% of your visibilities in a certain baseline length bins and distributed them elsewhere is tolerable. But when you come to a filling fraction of 0.25, so you have a 75% loss, then the systematic errors are intolerable. And so from these experiences, you can construct a set of criteria for how bad your BLDs are allowed to be before you have to really start worrying. And what we find is that, so as I already said, the azimuthally symmetric BLD defects that we have looked at so far are less disruptive. What is most disruptive is when you lose whole sectors of your sensitivity. And I'm going to come back to how we actually measure that. So, and the most severe problem that you can have in your UV coverage is really that you have incomplete tracks at the shortest baselines if you have extended emission. So if your object is bright over a large angular scale, and then it's often better to actually just flag the shortest baselines. If they're incomplete, if you have missing baseline orientations, just better flag them because it will otherwise screw up your entire image. So the lesson was that ALMA, the 12-meter array is only a snapshot instrument, so can only afford having no Earth rotation when you are in a compact configuration. But the 7-meter array and the extended 12-meter array configurations need Earth rotation to really get a very good beam shape at all angular scales. And so if you want to interpret your images correctly, you need to know what spatial and spectral information is actually contained in them. You can't just treat them like optical images. That is only really justified if you have a good UV coverage. And if your UV coverage is not good, this does not only affect individual spatial features, but also spectral features. Your line shapes will change. And so if you are lacking sensitivity at angular scales, which are important for your science goal, this all depends on your science goal, then you simply need more observations. But if you have enough sensitivity at all the relevant scales, but your UV coverage is maybe simply not rotationally symmetric enough, then your image may be ugly, but you may not have to give up on your data because there's still forward modeling. So I'm not going to go into this further, but you can simply simulate the array that was actually used to take your data and work from there, putting in models of your scientific target and send it through that appropriate array simulation and interpret your data in this way. You don't have to just image and work with the image. Okay, so as I already said, SSMS2 was this big effort that came out of this development study. And after the end of the development study, Darwin Lorber came here to ESO from the University of Vienna, thanks to the eMERGE group. And together with him, we put quite some work into extending the features of SSMS2. And now what came out of this is SSMS3. And the new features that were introduced were an improved support for 7-meter only data sets, both 7-meter only data sets and 7-meter plus 12-meter data sets, so groups with a 7-meter component. For that, we could only do 12-meter groups. And we introduced a new mode, which is what you have in this public version now, which is not intended for quality assurance, but for general UV coverage assessment based on the achieved rather than the expected parameters that come from your proposal. Because once you've got your data and it has been through quality assurance, these parameters are kind of met, but you might have, for example, done your own flagging and so on, or recalibrated or whatever, and then you may want, or you want to form your own data set as a new type of group. And then you're not really interested in the original expected parameters, but you want to base your assessment on the achieved parameters and just look at the shape. And that's what this new version offers you. There's also various other new functionality. For example, there's a new hour angle plot, so you can better understand how the scheduling was done of the data. There's also better handling of flag data, and there are some kind of convenience features like a collated PDF of the most important plots and better error handling, etc. So let's now start with the actual usage. So let's start with what comes out when you have run SSMS. So SSMS, when it's done, has produced a directory in your working directory that is called output_SSMS. And this directory contains 4 things. The most important one is the SSMS report. That's a text file that is essentially an excerpt from the CASA log of your session, containing only the most important entries, and in particular, a list of the UV coverage defects that were found. Then secondly, you have a whole bunch of PNG files, plots, diagnostic plots that illustrate these results that are mentioned in the report. And the most important of those are collated into a PDF file. So that's the first thing that you should look at. And then there's also the CASA log itself, which is the complete set of messages. Okay, let's now get into the various types of plots that SSMS produces. The first one is the one-dimensional baseline length distribution, where you see the observed one in blue, together with 2 expectations. One is a worst expectation and one is the best expectation. So what SSMS does, it fits the expectation shape to your observation and comes up with an angular resolution and the maximum recoverable scale. And based on that, it computes an expectation of what a tapered Gaussian with a nice point spread function would look like. And it computes that for the fitted AR range, sorry, for the fitted AR minus and plus 10%. So that's the best and worst AR. And those are shown here in black and green. And for a single MOUS, you have a bin width in this histogram that is constant. If you have a group, then bin width with increasingly widening bin width is used, so it increases linearly with baseline length, so that you have more resolution at the short end and more statistics, so to speak, at the other end. But that is really detailed. We come back to this in the example at the end. And then the next interesting plot is the same, but in 2D. So this is kind of the most iconic plot, so to speak, that came out of this development study. This is a 2D histogram of the weighted visibilities where the radius is the baseline length. The azimuth, so the polar angle, so to speak, in this 2D plot is the orientation of the baseline. And because the baseline is not a signed quantity, only 180 degrees of this plot are actually relevant. The other one, the other half is just a mirror, a point mirror of the other half. So in principle, you only have to look at these 4 sectors, or whichever you want. The other part is just a copy, but it's plotted because people are used to UV coverage plots being full circle. And the third dimension is then the filling fraction, so this ratio of observed over expectation. So ideally, this would totally be green, with filling fraction 1.0 everywhere, but this is essentially never achieved. And you can see here in red places where we have low exposure, so it's much less than what would be expected. And these kind of magenta and blue parts are where there's overexposure. For the 7-meter array, we use 6 equidistant bins, and for the 12-meter array, 10. And if you have a mixed array, so 7 and 12 meter, it will use 16 bins. The next plot is the 1D filling fraction plot. That is essentially the same as the previous plot. Sorry if I misspoke there, but in 1D. And what is nicely visible here is this typical U shape. So you have, typically with ALMA at least, an overexposure at the low and the high end. And in between, it goes down, and typically the filling fraction goes below 1. And then here, these other 2 lines are these limits that we derived in the development study for tolerable depletion, so to speak. In order to make the azimuthal symmetry better visible, this is now the same plot, but separately for each of the 4 azimuthal sectors. And ideally, these 4 lines should be on top of each other. Then you would have perfect azimuthal symmetry. But in reality, they never quite coincide. And so some sectors are more exposed than others. And you can see if they are dropout sectors, so if some sector is, for example, below the red line and doesn't have any sensitivity, and that is really a major problem there. To further investigate the azimuthal symmetry and quantify this further, we have introduced this plot here, which is called the azimuthal homogeneity plot, or inhomogeneity plot. So it shows, as a function of baseline, the value of the chi-square of a constant fit to the 4 filling fractions in one baseline length bin. So, for example, these 4 bins here, if you fit a constant function to the entries in them, then this function fit has a chi-square value, and that value is then entered here at the radius of this baseline. So this is the chi-square value 1.5. And if this goes above 2.0, then we say the inhomogeneity is not good. So in other words, there are some sectors missing exposure. or some are too overexposed. So this is about homogeneity, not absolute sensitivity. And what typically happens is that you have very good homogeneity at the short baselines, and then it gets worse and worse, and then maybe at the longest baselines it goes above 2.0, but not always. Now this next plot here is the new hour angle plot that was introduced in this version. So it simply always shows the hour angle range of the observation from -6 to +6 hours. 0 is north or south, depending on where your object has culminated. And the entries here are the same as in the baseline length distribution plots of weighted visibilities. So you don't really need to look at the absolute scale here, but just at the relative values. And so in this case here, we have an observation that was mostly taken at +2 hours hour angle. And this observation has a wider range at positive hour angles, but also a little more on the side before culmination. So ideally, you want to have a wide spread of hour angles, like from -4 to +4, with some kind of equal exposure to get perfect Earth rotation synthesis. Then for mosaics, there's also a special plot. This obviously only plotted when you have a mosaic. So it does a baseline length distribution for every mosaic field separately and plots them all on top of each other with different colors. And so you get, if everything is fine, you get a single line and you see only one color because they're all on top of each other. If things are not fine, then you see different colors with different BLD shapes, and then some mosaic pointings have a different UV coverage than others, and that's of course not good. But this has actually, I mean, we have seen very few examples in ALMA where this has happened. So this is really only a sanity check, but normally you don't even need to make this check. Just as a guidance, we overplot here this expected BLD shape. But what this plot is really about is the agreement between the BLDs of the different mosaic pointings. This next plot here is a very different one and was also one of the main outcomes of the development study. This is the so-called flat sensitivity plot. This shows something completely different from the other plots that we've seen so far. It's again plotted versus baseline length, but what you see here is something where for once smaller is better. So this is essentially a measure of the noise RMS that was achieved for this particular baseline length bin. So the smaller that noise RMS, the more sensitivity you have, obviously. But it's not the noise RMS itself, but it's the ratio of the achieved noise RMS and some expected noise RMS that is derived from an assumption that you have equal sensitivity over all accessible angular scales. And what you typically get here is this U-shaped plot where the lower end rises somewhere above 2. So you have twice the expected flat sensitivity RMS here at this lower end, and the same happens also at the upper end. And in fact, one can now derive from the position of where this intersection between the line 2 and the yellow line happens, what is the maximum recoverable scale and the angular resolution of this observation. So we have verified this by comparing it to the actual angular resolution and maximum recoverable scale measured via imaging and other means. And the agreement is extremely good. So this plot really has to be taken serious. And we try to improve the accuracy here by interpolating here with a parabola fit on both ends. So from this baseline length, together with the observation wavelength or frequency, you can then derive via this formula essentially the maximum recoverable scale and the angular resolution of your observation. And just to motivate this a little further, so it's essentially when your sensitivity is twice worse, then that essentially means compared to what happens here, this angular scale has become invisible. You're not sensitive to that really compared to what you are sensitive to here. Of course, you are still sensitive, but not with the comparable sensitivity that you have in the intermediate range, and so your range of recoverability really ends here. Realistically, that's the idea. Okay, those were the plots that I wanted to talk about. Next, we're going to talk now about the text output. So the text output is quite verbose. So if you look at the entire CASA log, it's very long. But the report is, as I already said, an excerpt from the log, and it essentially picks out what has this QA tag here in the log liner, in the logger line. And the most interesting parts in this version are the estimated maximum recoverable scale and your resolution from the flat sensitivity plot that we just talked about. So here in this example, for example, you have 7.8 arc seconds and 0.8 arc seconds for maximum recoverable scale and angular resolution. And then there can be a warning that this MRS is smaller than what was requested. What this requested here refers to is the value that was computed directly from the LO5. So there's an 11% discrepancy here, but you don't really need to worry about that. The very end of this report is then what is most interesting is the list of UV coverage defects. So it tells you the number, 9 coverage defects in this case, and it tells you also under which assumptions it computed those. So this was a 12 meter array. This was the representative observing frequency, and this was the expectation parameters it used to compute the filling fractions. And then it has, in this case, found these 9 defects. And these can be of the following types. So you can have individual BLD filling fraction values below 0.25 in one of those 40 bins or fewer bins for the 12 meter, for the 7 meter. And these can be regarded really as a minor problem if it's an individual BLD bin in one sector. Then there are messages about that the orientation is not homogeneous in azimuth in one radial bin. Also, that can be regarded as a minor problem, depending on how many of those you get. And then there's this message that that you have a filling fraction of less than 50% in the uppermost bin, so the one that is most crucial for the angular resolution. In one azimuthal bin, that is minor. But then the other errors that you might get, or not errors, defect messages are regarded to be major. And they essentially concern all defects that concern all azimuthal bins at once, so that happen everywhere, or all radial bins at once, so your whole sector. So if in either in a whole sector or in a whole radial bin you have individual filling fractions that are bad, you have to regard this essentially as a major error, and then you need to start worrying if that impacts your science goal and if you have to do something about it. Yeah, if you have a mosaic and this coverage is incomplete, this will also result in a warning. So coming now to the usage and how you actually install and run SSMS. I'm a bit over time, but we are done in a very short moment. So that in principle is described very well on this web page. So I'm going to only mention here that you have to download the tarball, you have to unpack it obviously, and then you go into the directory that you created, and you edit this script, run SSMS public, and in there you essentially only have to edit this part here that is has this placeholder value, your path here, and there you have to put the absolute path, so starting with a slash, of the location of this directory that you have unpacked here. So the location where SSMS.py and the others can be found. And then to run the whole thing is very simple. You put your measurement sets into a directory, and you call casa in this way, and that's it. It finds the measurement sets automatically, and you have essentially to give no input parameters. If you want to override the default pattern that is used to identify the measurement sets, which is star.ms.split.cal, you can do that here with this -p parameter, and for example, this way. Yeah, that's it already in terms of usage. So we try to keep it very simple. And now I'm going in the last 5 minutes. Sorry if I'm a bit over time. I'm going to now talk about one example, and that is one where you actually assess a group ops unit set. And the one in our example is going to be one composed of a TM1 and a 2M2 observation, but supported are also TM1 and 7 meter and TM1 and TM2 and 7 meter. So essentially all groups, all possible groups, except those that have a total power component. Of course, you can run it on the part that is not a single dish, but yeah, you're going to not have any information about the single dish component in the output. So the recommended procedure here is that you place the calibrated MSs for each MOS in separate directories, and then you run SSMS on them separately and check the report, and then you do the same thing again with all of them together in one directory. So you run SSMS on the entire group, and then you check the output for the group. And you need to wonder, is the angular resolution that I get in this whole group now still sufficient, because it's possibly going to be slightly worse than what you get only from the TM1 or the most extended configuration that's included. Do you have the maximum recoverable scale that you need is the other question you need to ask. And then were there any UV coverage defects? Okay, let's go through one example. So in my example here, I have created a directory called SSMS3. I go in there, I download the table of the distribution, I unpack it, I do this editing. Of course, you have to do this only once, not for every assessment you want to do. And then I make those 3 directories, TM1, TM2 group, to put my various calibrated measurement sets inside. You can work with soft links so that you don't have to duplicate the data on your disk. And then I have a setup that looks like this. So one group directory containing the TM1 and TM2 measurement set together, then only TM1 and only TM2. And here's my distribution directory with the code of SSMS. And now I cd into the first of these three directories and I run SSMS. It finds the measurement set. It tells me, okay, this is the SBU ID that is related to it. And then comes some less important output. And at the end, I already on the terminal get essentially this list of defects that was found and the MRS and AR. And so our 2M2 observation has quite a few minor problems. And for example, this one here, we have 3 times filling fraction below 0.25 in the same baseline length range from 30 to 40% for different azimuths. And that is really bordering on a major problem. So not great. For the TM2, if I do the same thing, I get a much shorter list of defects. So this is really nice, no major problems. So the TM2 data is fine, the TM1 has problems. And if I now run this whole group, so I'm going to the group directory and run the same command again, then it finds that these two measurement sets are from 2 different SBU IDs and it has identified that this is a group. But then further down, the output format is essentially the same. So we get again an estimate of the MRS and the angular resolution. And here the MRS is 4.97. For the TM1, it was 3.9. For the TM2, it was essentially 9. So this estimate is somewhere in between. That is expected. And one has to see, I mean, as I already said, this number here is slightly flexible, but it's somewhere definitely better than this. Maybe not quite as good as what TM2 alone gives you. And for the angular resolution, we find that it's slightly worse than what you get from TM1, but not much. So that's great. But we have inherited all the problems from the TM1 observations and even more. So now we have in 2 baseline length range bins defects in 3 different azimuthal bins. So that doesn't look great. And now you should really look at the plots to confirm. And so those plots you find in these output SSMS directories that were created in the 3 working directories. And in there you find these collated PDFs, one for the TM1, one for the TM2, one for the group. And let's just have a look at a few here. So for the group, the 2D filling fraction plot is actually pretty bad. It's underexposed for the intermediate baselines and overexposed for the long baselines. The homogeneity in azimuth is fine, but you have this kind of really bad dip in the middle, as we already expected from the TM1 analysis. And the same is also visible in this per sector filling fraction plot and also in the observed and expectation BLD plot. So the blue again is the observed, the black and green is the expectation, and there's this huge shortcoming here that also results in the flat sensitivity plot in this bump that is very unusual. And so if you image this, you get a quite non-Gaussian PSF. And so ideally you should try to fill this with more observations near 750 meter baseline length. And looking again at these baseline length distributions from TM1, TM2, and the group, we can see that this is really all due to the shortcomings of TM1. The TM2 observation has the longest baseline of something like 500 meters and actually doesn't contribute anything beyond here. or here in this plot. So this dip here is essentially transferred 1-to-1 over here. And yeah, there's nothing that data combination of these two can do about it, because the TM2 is only adding to these observations here at the bottom. So you're extending your maximum recoverable scale, but you're not fixing anything at the intermediate baselines. And I want to stress that I picked this example in order to show you what a bad defect looks like. Normal ALMA data doesn't have these extreme defects. This is really extraordinary. I've seen this in very few data sets. So really a handful only. Okay, last slide. Please try to use SSMS on your data and give feedback, ideally via help desk tickets. Also, if you need any help with this in interpreting the output and so on, please file a help desk ticket. The next big step that I see in terms of improvements is support for a total power component. Then we would have really achieved the goal of a assessment tool for every type of group ops unit set. But probably we will also think of other improvements with the help of your feedback. And so there will be updates and patches in the future to SSMS 3.0. And there will be releases maybe every half a year or so. And you will be notified when that happens. It will be on, I mean, this page that I mentioned will stay, and updates will be published there as well. Okay,